A mountain of stone stands silent in the desert, a puzzle built over 4,000 years ago. How ancient engineers moved stones without modern technology is one of history's most captivating mysteries. By the end of this journey, you will understand the lost principles that allowed humans to build the impossible. We will uncover how sound might have levitated blocks and why some stones may not be stones at all. What does true ingenuity look like when you have nothing but the natural world and your own mind to work with? That first and most powerful technology was a profound understanding of the materials themselves. Before a single stone could be moved, it had to be freed from the earth. Picture a team of workers at a quarry, armed not with dynamite and machinery, but with wooden wedges, stone hammers, and an intimate knowledge of the rock's secrets. Their primary tool was thermal shock. They would build a small fire directly against the granite or limestone face. Once the rock was searing hot, they would douse it with cold water. The rapid contraction caused the stone to crack along natural fault lines, creating a clean, workable block. It was a delicate art, a conversation with the stone itself, listening for its weaknesses and using the elements to persuade it to break. This was not mindless labor, it was applied physics. The precision of these initial cuts is staggering, often leaving surfaces so smooth that later fitting required minimal effort. So, with a multi-ton block now separated from the living rock, the real challenge began: how to move an object heavier than anything in their world. A single worker with a long wooden pole could lift the corner of a stone slab weighing many tons. This seemingly simple action reveals a profound truth understood by builders across the ancient world: the power of leverage. By placing a pivot point or fulcrum in just the right spot, the length of the lever multiplies a person's strength exponentially. A small team, using nothing more than timber and coordination, could hoist weights that defied human scale. This principle was often enhanced with counterweights. Imagine heavy baskets filled with sand or smaller stones, suspended from a primitive crane. As workers carefully removed sand from one basket, it would act as a controlled counterweight, allowing a massive block to be tilted, raised, or gently lowered into a perfect fit with breathtaking precision. The Greek inventor Archimedes captured the sheer potential of this idea when he declared that with a lever long enough and a place to stand, he could move the entire world. This was not just a theoretical boast, it was a reflection of the practical genius that built pyramids and temples. Mechanical advantage was the silent partner in every lifting operation, turning impossible tasks into manageable steps. But lifting a block is only one part of the challenge. The next step was to move it, and for that, ancient engineers turned their attention to the ground beneath their feet, mastering the art of the inclined plane. That grueling horizontal pull required its own form of genius. The solution was not to fight friction, but to outsmart it completely. Ancient engineers transformed the very ground the stones moved over, creating a low-friction highway. The most common method involved laying a path of wooden rails like primitive railway tracks. Workers would pour a slurry of water and clay ahead of the massive stone sled, turning the surface into a slick, muddy lubricant. This simple mixture drastically reduced the dragging force needed. Experiments show that with this technique, a team of just a dozen people could pull a multi-ton block. But some cultures took this concept even further. In places like Malta and on Easter Island, evidence points to the use of stone ball bearings. Carefully carved stone spheres were placed in parallel tracks, and the massive stone blocks were then levered on top of this rolling foundation. Instead of a continuous, grinding drag, the stone was now rolling forward with relative ease. This was not just about moving a heavy object, it was about redefining the relationship between the load and the path it traveled. Yet, even with rails and rollers, the sheer human effort involved was immense. This leads to a profound question: how did ancient cultures coordinate hundreds of workers to pull in perfect unison? The answer may lie not in a tool you can hold, but in one you can hear. The ground itself became a machine. This was the fourth principle, a masterclass in environmental engineering where the landscape was not an obstacle but an active participant. Imagine a long, gently sloping ramp made of earth and brick, leading directly to the rising wall of a pyramid. This was the tool that turned vertical impossibility into a manageable, gradual ascent. Workers, or sometimes oxen, would drag the heavy sledges up these earthen causeways, their progress slow but steady. The true brilliance of the ramp system lies in its adaptability. For the Great Pyramid, Egyptologists suggest a spiraling internal ramp may have been used, corkscrewing up the inside of the structure and allowing blocks to be hauled right to the very top, all from within the pyramid's own shell. But the ingenuity did not stop at ramps. In some swampy regions of Europe, ancient builders created entirely new terrain. They constructed trackways of bundled brushwood and logs, laying a stable road across soft, unstable ground. This transformed impassable wetlands into a reliable highway for transporting stones that weighed many tons. It was a complete rethinking of the problem, moving not just the stone, but the very path it traveled on. Yet, even with these brilliant physical systems, a question remains: how did they achieve such impossible precision with such seemingly simple tools? The answer may be written in the sky, but what if the very stones themselves are not what they seem? A fourth principle emerges from the edge of mainstream archaeology, a theory so radical it reimagines the fundamental nature of ancient construction. This is the idea of geopolymer, or artificial stone. What if the immense blocks of the pyramids were not dragged from quarries, but were instead cast in place, much like modern concrete? Proponents of this controversial view suggest that ancient engineers discovered a chemical recipe, a process that could turn common limestone clay into a man-made stone. They would have crushed the soft, natural material, mixed it with water and a specific alkali activator, perhaps derived from ash, to create a thick, pourable slurry. This mixture was then carried in baskets to the construction site and poured into wooden molds, where it would harden over time into a solid block. This would explain the almost supernatural precision of the joints, with blocks fitting so perfectly that not even a razor blade can slide between them, as if they were fused together from a liquid state. It would also account for the mysterious presence of air bubbles and organic fibers found inside some pyramid stones, elements you would not expect to find in solid, quarried limestone. If true, this method would have been a logistical revolution. The back-breaking labor of moving multi-ton blocks across the desert would be replaced by the simpler task of transporting bags of powdered rock and water. While this theory is hotly debated and far from universally accepted, its power lies in its challenge to our assumptions. It forces us to consider that ancient ingenuity may have extended into the realm of chemistry, creating materials that have fooled us for millennia. From this speculative frontier of chemical innovation, we return to a method of pure, coordinated human power, a symphony of movement that may have been guided by an unexpected tool. The sheer scale of this human machine was its own form of technology. To move a single colossal obelisk required the perfectly synchronized effort of hundreds, perhaps thousands, of individuals. They were not just a mass of laborers, but a meticulously organized system, divided into specialized teams. One group pulled on the main hauling ropes, another stood ready with levers to guide the stone's path, and others ensured the rollers or sledges remained in place. The true marvel was the rope they used, each one an engineering feat in itself. Craftsmen wove thousands of strands of papyrus or flax into massive cables, creating tensile strength capable of withstanding forces that would snap modern steel cables. But the strongest rope is useless without perfect coordination. The success of the entire operation hinged on rhythm. A head foreman, likely using a drum or a horn, would set the beat for a coordinated heave. With each unified pull, the massive stone would inch forward, a testament to what disciplined collective action could achieve. This human symphony turned individual effort into a single, unstoppable force, capable of navigating the stone through its most challenging transitions. Yet, even with this incredible coordination, some stones were moved in ways that seemed to defy our understanding of physics altogether. For stones traveling vast distances, the river became a liquid road. Water offered a fundamental advantage over land buoyancy. A multi-ton block that would sink into the earth or crush a wooden sledge became almost weightless when supported by a boat. Ancient engineers understood this principle perfectly, often establishing quarries right on riverbanks or going to the extraordinary effort of digging canals directly to their construction sites. This created a seamless aquatic highway for materials. The Egyptians masterfully synchronized their building projects with the rhythm of the Nile. They would load massive granite blocks onto specially designed barges during the annual inundation, when the floodwaters rose and spread across the land. This allowed them to float stones right to the edge of the desert plateau, dramatically shortening the final, grueling overland pull. Half a world away, the builders of Angkor Wat executed an even more ambitious aquatic plan. They constructed a vast, intricate network of canals and reservoirs that served as the lifeblood of the city. These man-made waterways were not just for irrigation or ceremony. They were the primary freight system for the sandstone blocks needed to build the temple's majestic towers. The logistics were immense, requiring precise management of water levels, strong and stable barge designs, and clever docking procedures to unload the stone. Yet, for all its efficiency, this method presented one final, critical puzzle. After a smooth journey by water, how did they transfer these colossal weights from the rocking deck of a boat onto the solid, unmoving earth? The most elusive principle of all seems to defy the very laws of physics. Scattered through ancient legends are whispers of a technology that did not fight gravity, but simply asked it to step aside. Tibetan and Egyptian texts speak of monks and priests using specific chants, the resonant beat of a drum, or the pure tone from a metal disc to make massive stones lose their weight. According to these stories, a large block would become light as a feather, gliding through the air on a carpet of sound, moved into place by just a few individuals. To our modern scientific minds, this sounds like pure myth. Yet, laboratory experiments in acoustic levitation show that powerful, focused sound waves can indeed create a pressure field capable of suspending tiny droplets of water or small pieces of solid matter in midair. The science is real, just on an incredibly small scale. The tantalizing, unproven question is whether an ancient civilization could have mastered this principle on a monumental level, using vibrations we can no longer replicate or even perceive. This remains a fringe theory with no physical evidence like a sonic tool ever found at a construction site, but its power is not in its proof, it is in the challenge it poses. It forces us to wonder if we have lost entire branches of knowledge, understanding of energies and natural harmonies that have since fallen silent. While the stones did not float into place on waves of song, the very existence of these legends points to a universal human longing to solve an impossible problem with a beautiful, almost magical solution. From this ethereal frontier of lost science, we ground ourselves in a far more practical and clever manipulation of the elements, one that harnessed the power of ice. The sheer power of the ox became a living engine for ancient construction. Across the empires of Egypt and Mesopotamia, teams of these patient animals were the primary source of traction for moving the heaviest stones. Their immense strength was harnessed to pull massive sledges along lubricated tracks, turning a task that would require hundreds of people into one managed by a handful of drivers. But this partnership was far more sophisticated than simply tying a rope to an animal. It required brilliant innovation in tackle. Early yokes that pressed against the throat could choke an ox, drastically reducing its pulling power. Ancient engineers developed padded chest harnesses that distributed the load across the animal's strong shoulders and chest, allowing it to put its full weight into the pull without harm. This was a crucial advancement, a perfect marriage of zoology and engineering that respected the animal's body while maximizing its potential. In the Americas, without access to oxen, builders demonstrated remarkable adaptability. The Inca, masters of the high Andes, used trains of sure-footed llamas to carry smaller, precisely cut stones up steep mountain paths to build sites like Machu Picchu. Each animal carried a manageable load, but together, in a long caravan, they formed a relentless supply chain moving across impossible terrain. This global perspective shows that the principle was not about having one specific animal, but about intelligently leveraging the strongest local resources. By domesticating and understanding these creatures, ancient societies effectively created a renewable, biological technology that multiplied their own capabilities many times over. This powerful collaboration between human will and animal muscle found its perfect complement in a deceptively simple wooden machine. That simple lever used to lift water from the Nile contained the seed of a revolutionary idea. The shadoof, with its bucket on one end and a counterweight on the other, proved that a person could lift a heavy load with minimal effort. This principle of balanced force was the foundation for one of antiquity's most transformative machines, the wooden crane. Greek engineers, building on this knowledge, achieved a monumental leap forward with the invention of the compound pulley. Attributed to the brilliant mind of Archimedes, this system used multiple wheels and a single rope to create an astonishing mechanical advantage. With a series of pulleys, a single individual pulling on a rope could slowly but surely hoist a stone block that weighed many tons. The story goes that Archimedes, demonstrating the power of his device, single-handedly pulled a fully loaded ship ashore. While these machines were built from wood, their construction was a masterwork of joinery. Craftsmen used mortise and tenon joints, carefully carved to interlock with incredible strength, creating a flexible yet robust framework that could sway and absorb stress without shattering. Ropes woven from resilient materials ran over wooden sheaves, transferring the pulling force through the pulley system. You can see the legacy of these cranes etched into the stones of Greek temples and Roman theaters, where massive blocks were precisely set into high walls. Each lift was a slow, deliberate ballet of human power amplified by simple physics. This evolution from the basic shadoof to the compound pulley shows a clear and deliberate progression in human thought, a deeper understanding of how to manipulate force. Yet, for all its power to conquer height, the crane was a machine of vertical ascent. To conquer distance, ancient engineers devised a system of movement so fluid it turned solid ground into a temporary river. This quiet dance of balance and leverage transformed unwieldy stone into something almost graceful. For the final, delicate act of positioning, ancient engineers mastered the strategic use of pivots and fulcrums. Once a massive block was near its destination, the challenge shifted from raw movement to finesse. The solution was deceptively simple. Workers would use levers to lift one end of the stone, just enough to slip a rounded river rock or a carefully shaped, lubricated wooden pivot underneath. With this central point of contact established, the multi-ton block could be rocked back and forth, walked incrementally into its perfect final position. Think of it as carefully nudging a heavy piece of furniture across a room by tilting and pivoting it from one corner, rather than trying to shove the whole weight at once. This method granted them incredible control, allowing for adjustments so minute they could align a stone within a fraction of an inch. It was a physical conversation with the block, a continuous readjustment of balance and force. This technique demanded a deep, intuitive grasp of the stone's center of gravity. A miscalculation could send the block tipping dangerously off its pivot, but a perfect understanding turned an immovable object into something manageable. This precise control was absolutely essential for fitting giant lintels over doorways or locking the final, capstone pieces into a vaulted ceiling. Watching a modern stonemason use the exact same rocking method today is to see a living thread connecting us directly to that ancient ingenuity. Such flawless physical execution, however, points to a hidden layer of planning, a precision that could only come from numbers and calculation. The stones themselves are a testament to a hidden language of numbers and angles. This silent, cerebral work was the invisible blueprint for every physical act of construction. The perfect square base of the Great Pyramid, aligned with the cardinal directions with an error of less than a single degree, was not a lucky guess. It was the product of a deep, practical understanding of geometry. Ancient surveyors used simple but brilliant tools to achieve this impossible accuracy over vast distances. A leveled wooden frame filled with water created a perfect horizontal reference. A weighted plumb line gave them a true vertical. With these, they could establish a foundational plane as flat as any modern laser level. To create perfect right angles for a pyramid's corners, they used a simple knotted cord. By tying knots at precise, equal intervals, they could stretch the rope to form a 3-4-5 triangle, a classic application of the Pythagorean theorem centuries before Pythagoras was born. This guaranteed a perfect 90-degree angle every single time. The very dimensions of the pyramids often encode mathematical constants like pi, the ratio of a circle's circumference to its diameter. This suggests these builders were not just stacking stones, they were embedding fundamental truths of the universe into their architecture. This mathematical foundation was essential for the logistics, too. They could calculate the volume of a ramp needed to reach a certain height, or precisely estimate the number of workers and the amount of food required for a decade-long project. This was more than engineering, it was a form of applied philosophy, a belief that the universe was orderly and that humanity could mirror that order in stone. Such grand, coordinated efforts on a civilization-wide scale point to one final, crucial element, the social machine that made it all possible. The true engine behind every stone was the society that moved it. Beyond the levers and ramps, the most sophisticated technology of the ancient world was its social organization. To build a pyramid required a complex administrative machine capable of managing thousands of people for generations. Evidence from worker villages like Deir el-Medina in Egypt reveals a surprisingly structured world. These were not grim labor camps, but functioning communities with bakeries, infirmaries, and comfortable housing for the skilled artisans and their families. The state provided a steady supply of bread, beer, fish, and vegetables, ensuring the workforce was healthy, stable, and motivated. This was not slavery, but a form of national service, a rotating corps of conscripted laborers who worked in organized shifts. They were farmers who came to work on the Pharaoh's project when the Nile's flood made their fields untouchable, contributing their labor to a monument they believed would ensure the cosmic order of their entire civilization. The project itself was broken down with brilliant logistical insight. Competing teams, each with its own name and identity, were assigned specific sections of the pyramid. This created a powerful sense of pride and friendly rivalry, turning an overwhelming national project into a series of manageable, personal accomplishments. You can almost hear the shouts of encouragement as one team raced to lay their course of stones faster than the team working alongside them. This human engine was fueled by more than just rations. It was powered by a shared belief in the work and the practical, on-site innovations that made their daily lives possible. The administrative scribes who tracked every loaf of bread and every block of stone were as vital to the project as the strongest quarrymen. They were the ancient equivalent of a project management software, using hieratic script on papyrus to coordinate a supply chain that stretched across the entire kingdom. This intricate social machine, so carefully designed and maintained, raises a final, humbling question. If we could see past the stones to the society that built them, what other secrets about our own potential for collective action might we uncover? The most intelligent transportation system sometimes meant not moving the stone at all. Ancient builders were deeply practical geologists, and their first strategic decision was always about location. They would choose a construction site based on the raw materials available right there, turning the landscape itself into their primary quarry. The magnificent city of Petra stands as the ultimate example, a breathtaking metropolis not built from stone but carved directly into the face of a living mountain. Every column, staircase, and chamber was sculpted from the cliffside, eliminating the need to move colossal blocks across any distance. This principle of on-site sourcing was a global strategy. The Romans frequently established their quarries just a few miles from their building sites, creating short, manageable supply lines for their aqueducts and amphitheaters. This was not just about convenience, it was about a profound understanding of material properties. When a specific type of stone was essential, like the beautiful red granite from Aswan for Egyptian obelisks, they selected it with purpose. They sought out rock that was durable enough to last for millennia, yet still workable with their copper and stone tools. Their genius lay in knowing how to read the stone. They would identify natural fracture lines, weaknesses, and bedding planes in the rock formation. By driving wooden wedges into these pre-existing cracks and soaking them with water, the expanding wood would persuade the stone to split along a clean, predetermined line. This method allowed a small team to liberate a perfectly shaped multi-ton block with an efficiency that seems almost supernatural. It was a conversation with the earth, a negotiation that respected the stone's inherent structure. This intelligent use of local resources was the invisible foundation of every great project, proving that the most advanced engineering often begins with the wisdom of using what you already have. Water itself became a tool for conquering friction, its properties harnessed in brilliant opposition. In the freezing north, builders turned to the power of ice. They would patiently wait for winter's grip, then drag massive stone sledges along paths they had deliberately soaked and frozen. As the colossal weight began to move, teams might even spray water ahead of the sledge, continuously renewing the surface into a slick, near-frictionless track of ice. The stone would glide as if on a polished mirror, a simple yet profound manipulation of the natural world. Meanwhile, in the scorching deserts, the very same element was used in a completely different way. Here, workers poured water onto the sand directly in front of a heavy sledge. This wasn't to create ice, but to bind the loose grains together. The dampened sand formed a firm, compacted roadway that prevented the sledge from digging in and getting stuck. In other instances, they created a slippery slurry of mud and water, effectively turning the ground into a natural lubricant that allowed the sled to slide with remarkable ease. This global ingenuity reveals a deep understanding of physics. Whether using water's solid form to reduce friction or its liquid form to create stability, ancient engineers were masters of phase change. They observed the world around them and asked a simple, powerful question: how can this element in this place make the impossible possible? This pragmatic magic of ice and mud feels almost tangible, a technology we can still see and touch. But what of the methods that left no physical trace, the ones that seem to belong to the realm of pure myth? One of the most audacious ideas suggests they commanded the wind itself. The Kite Hypothesis proposes that ancient engineers used massive, purpose-built sails to harness the desert breeze, turning an unpredictable natural force into a lifting engine. In a modern test of this theory, a team of researchers and engineers successfully raised a multi-ton obelisk using a large kite and a cleverly designed pulley system. The experiment proved that a strong, steady wind could generate enough sustained lift to do the work of hundreds of people. While no ancient kite has ever been found, some researchers point to enigmatic carvings and local legends as potential clues. A faint inscription might not show a team of laborers, but a giant, curved shape towering over a stone block. A folk tale about a magical flying carpet could be a poetic memory of a stone slab gliding into place. To make this work, these builders would have needed an intuitive mastery of aerodynamics. They would have understood how to design a kite with the perfect balance of lift and stability, crafting it from woven papyrus or linen to create a wing vast enough to catch the power of the sky. The coordination would have been a breathtaking spectacle. A ground crew holding guide lines as thick as your arm would have had to work in perfect harmony with the wind's gusts and lulls, easing the colossal weight upward with a control that feels almost impossible. This idea stands at the very edge of accepted history, a beautiful and unproven thought experiment. Its power is not in its certainty, but in its challenge to our imagination. It dares us to consider that the first successful aircraft might not have carried a person, but a piece of a pyramid. After looking to the air for answers, we find a method that is far more grounded, using the Earth's own stability as the ultimate foundation. The ground beneath their feet was not a fixed obstacle but a material to be reshaped. Ancient engineers understood that the most direct route was not always the most efficient, and their greatest innovation was sometimes the path, not the vehicle. Across the boggy wetlands of Neolithic Europe, they built trackways, intricate roads constructed from split logs laid side by side across the soft, unstable peat. These wooden pathways transformed treacherous, sinking ground into a solid, reliable highway, allowing communities to transport goods and materials that would have otherwise been swallowed by the earth. This was a profound investment in infrastructure, a commitment to permanently altering the landscape for future generations. The same principle of preparing the stage was applied on a grand scale for moving the colossal Moai statues of Easter Island. Researchers propose that the islanders prepared carefully leveled and reinforced roads, clearing the route of any major obstructions. The famous walking method, where teams used ropes to rock the multi-ton statues from side to side, would have been impossible without this meticulously prepared foundation. Each small, controlled tilt required a stable, predictable surface to prevent the statue from tipping into an uncontrolled fall. The road itself became a precision tool, its smooth, compacted surface enabling a delicate dance of balance and momentum. This approach reveals a sophisticated two-part strategy: the creation of a specialized tool for movement, and the simultaneous creation of a specialized environment for that tool to operate within. The immense effort spent grading and clearing these roads was not wasted time. It was an essential multiplier of human effort, turning a potentially chaotic and dangerous maneuver into a repeatable, controlled process. After such grand modifications to the very earth, The final act of placing a stone demanded a different kind of precision, one achieved with the simplest of wooden tools. The true power of these ancient projects lay not in complex machinery, but in the patient, masterful application of simple tools. A copper chisel seems impossibly soft against granite, yet in the hands of a skilled artisan, it became a precision instrument. The secret was not brute force, but an understanding of the material's own weaknesses. Workers would use a harder stone, like dolerite, to repeatedly pound a straight line across the granite surface. This process, called pecking, created a fragile groove. Then, the copper chisel was used not to cut but to pry, levering out small fragments along this pre-weakened line. It was a dance of persistence, a slow, deliberate conversation with the stone. For the final, breathtaking finish, they turned to nature's own abrasives. Quartz sand, which is harder than granite, was poured onto the surface. Using a flat piece of wood or stone, workers would sand the block back and forth for days, even weeks, gradually grinding it down to a polish so flawless it could reflect the sun. This was not a quick process, but a testament to a culture that measured its achievements in generations, not quarterly reports. The sophistication was never in the tool itself, but in the accumulated knowledge of how to use it, knowledge passed from one craftsman to the next over centuries. This deep, physical connection to their materials suggests they saw the world in a way we have perhaps forgotten. They understood the hidden qualities of stone, water, and wood, and this intimate knowledge may have been guided by a force far greater than themselves, a celestial blueprint written in the stars. The sky itself was their ultimate blueprint. Many of the world's most enduring stone structures are locked in a silent, perfect alignment with the sun, moon, and stars. This celestial choreography was far more than spiritual observance. It was the master clock for the entire construction process. A deep understanding of astronomy provided the most accurate calendar imaginable, allowing ancient project managers to synchronize their monumental tasks with the rhythms of the earth. In Egypt, the annual flooding of the Nile was not a disaster, but a scheduled event. The rising waters created a natural highway, and the master builders timed their work so that massive stones loaded onto barges could be floated right to the construction site as the floodplain reached its peak. This turned an obstacle into an opportunity. Similarly, quarrying operations were likely scheduled for the dry season, when the ground was firm and stable, making it easier to transport multi-ton blocks on sledges without them bogging down in mud. The stars also served as a celestial compass to lay out the near-perfect square base of the Great Pyramid, which is aligned to the cardinal directions with an error of less than 1/15 of a degree. The builders needed a fixed, unwavering reference point. They found it in the circumpolar stars, which never set, rotating around the true north celestial pole. By sighting on these eternal markers, surveyors could establish a true north-south axis across miles of open desert, a feat of precision that still baffles engineers today. This integration of cosmic knowledge with earthly labor reveals a holistic worldview. The practical act of moving a stone was not separate from the spiritual order of the universe. It was a direct expression of it. Every perfectly placed block was a statement that humanity could build in harmony with the cosmos, creating a sacred geometry on earth that mirrored the heavens above. This intimate conversation with the stone began with knowing its very soul. Ancient engineers did not see a block of granite or limestone as an inert obstacle. They understood it as a material with a unique personality, with strengths to be harnessed and weaknesses to be gently persuaded. Their knowledge was a deep, empirical science, cultivated over centuries and passed like a sacred trust from one generation of masons to the next. They learned through meticulous observation which specific type of limestone became softer and more workable when saturated with water, a property that allowed for smoother carving straight from the quarry face. They mastered the art of thermal shock, not as a crude force but as a precise tool. By building a controlled fire against a granite surface and then dousing it with cold water, they could guide fractures along the stone's natural crystalline planes, effectively convincing the rock to split itself along a predetermined line. This was not a battle of wills but a collaboration. They knew to seek out dense, fine-grained stones for foundations, where immense weight and stability were required, and to reserve more easily carved varieties for the intricate reliefs that would adorn the walls. This wisdom was their true inheritance, a living library of material behavior that turned impossible construction into a repeatable craft. This profound, hands-on relationship with the physical world is something modern industry, with its standardized steel and concrete, has largely left behind. Their empirical science, born of endless trial and error, was every bit as valid and sophisticated as our own laboratory-tested data, and this was not a secret held by a single, isolated culture. The very same principles of material mastery emerged independently across the globe, a universal language of stone spoken by builders from every continent. This shared language of stone speaks to a deeper truth about human ingenuity. Across vast oceans and impassable mountain ranges, separated by thousands of years and entirely different cultures, ancient builders kept arriving at the same elegant solutions. The lever, the ramp, the roller, these are not inventions that belong to any one civilization. They are fundamental responses to a universal problem, a collective human intellect working through the same physical constraints. A builder in Mesopotamia wrestling with a multi-ton statue and an engineer in Mesoamerica fitting a limestone block for a temple platform would have understood each other's work instantly. They both knew that a long, sturdy pole and a pivot point could grant them the strength of a giant. They both understood that a gently sloping path of earth could conquer a vertical cliff face. This points to one of history's great debates. Did this knowledge arise independently in the brilliant, isolated minds of each culture, or did it travel along the invisible threads of early global connection? The wheel presents a fascinating clue. While many megalithic cultures did not use the wheel for transporting their heaviest stones, they were intimately familiar with the principle. The potter's wheel was a common technology, a spinning platform that relies on the exact same concept of rotary motion. This suggests the core idea was present, but its application was a matter of practicality. Perhaps dragging a sledge over a prepared track was simply more efficient for a 60-ton block than trying to build a wooden axle strong enough to support it. Yet we cannot ignore the potential for knowledge to travel. Skilled artisans were highly prized, often moved across empires as spoils of war or as honored guests. Trade routes like the famed Silk Road were not just conduits for spices and silk, they were highways for ideas. A master stonemason from one kingdom, sharing techniques with another in a distant land, could have sparked a revolution in local building methods. This cross-cultural exchange does not diminish their achievements, it enriches them. It reveals a world more interconnected than we often assume, where a breakthrough in one region could ripple outwards for centuries, blending with local genius to create something entirely new. This global tapestry of innovation highlights our common drive to leave a mark on the world, a universal ambition carved not just in stone, but in the very principles we use to move it. Such widespread ingenuity relied on a final, deceptively simple method, one that transformed the passage of time itself into a constructive force. That slow, grinding rotation was a testament to endurance over explosive power. For the final, precise lifting of impossibly heavy stones, ancient engineers turned to the capstan. Picture a massive wooden drum set vertically into the ground with long wooden bars inserted into its top like the spokes of a giant wheel. A team of workers would walk in a continuous circle, pushing against these bars, their collective effort turning the drum with a steady, inexorable force. A strong rope tied to the stone load was wrapped around this rotating spindle. With each full rotation, the rope wound tighter, hoisting the multi-ton weight upward in a slow, perfectly controlled ascent. This method provided a tremendous mechanical advantage, turning the rhythmic, walking pace of a few individuals into the lifting force needed to raise a stone that weighed as much as a small house. The true genius of the capstan was its control. Unlike a single, frantic heave, this system allowed for minute adjustments. The stone could be lifted an inch, paused while its alignment was checked, and then raised another inch with absolute precision. This would have been absolutely essential for a task like placing the massive lintel stones atop the uprights at Stonehenge, where a mistake of even a few centimeters would have been catastrophic. The work was slow, monotonous, and physically demanding in a way that tested the spirit. It required a different kind of strength, not the quick burst of a lever, but the deep, patient persistence to keep walking that circle, hour after hour, until the job was done. This intimate, grueling collaboration with simple machines stands in stark contrast to a theory that suggests some builders manipulated the very landscape, treating it not as a static stage, but as a dynamic, pliable material. The sheer perfection of a single stone at Pumapunku feels impossible. Each block is a geometric puzzle with razor-sharp edges and complex, interlocking channels cut into hard andesite with a precision that mirrors modern machinery. For some, this level of workmanship is a siren call, pointing to a chapter of human history we have somehow missed. The theory of a lost civilization suggests that a sophisticated society, possessing knowledge we would consider advanced, once existed long before our accepted timeline. Its legacy, according to this view, is embedded in the stonework of sites that defy simple explanation with the tools we traditionally attribute to their builders. Mainstream archaeology offers compelling counter-arguments, attributing these wonders to the incredible skill of the known Tiwanaku culture, using stone tools, patient abrasion, and generations of accumulated craft. Yet the lost knowledge theory persists not as proven fact but as a powerful question mark. It challenges us to consider the fragility of history itself. Entire libraries of human ingenuity can vanish, leaving behind only silent stone riddles that whisper of what might have been. This speculation invites a humble openness, a readiness to question our assumptions about the past. Beyond these grand mysteries of lost worlds, we find a technique of such elegant simplicity it feels almost like a secret handshake between the builder and the earth. The pyramid itself may have been the very machine that built it. A compelling theory for the Great Pyramid's construction proposes an internal, spiraling ramp corkscrewing up within the monument's growing core. Instead of erecting and then painstakingly dismantling colossal external ramps that would have required more material than the pyramid itself, the builders could have used the structure's own body as a permanent roadway. As each new course of stones was laid, the ramp would climb with it, a hidden, ascending tunnel through which teams hauled blocks right to the summit. This elegant solution transforms our view of the pyramid from a static object into a dynamic process, a living construction site where the finished product and the building method were one and the same. While direct archaeological evidence for this internal ramp remains elusive and fiercely debated, its power lies in the logistical problems it solves. It explains how such precision was achievable at such extreme heights without the footprint of an enormous, sloping mountain of earth extending far out into the desert. Modern engineers, using computer models, have shown the idea is structurally feasible, revealing how ancient planners might have thought in 4 dimensions, integrating time and movement into their architectural blueprint. This theory is a perfect example of how our understanding of the past is not set in stone, but is itself a dynamic structure, constantly being reshaped by new questions and insights. It forces us to see the pyramid not just as a tomb, but as a testament to a fluid, adaptive intelligence, where every stone laid was also a path forged for the next. Every movement of a colossal stone was a negotiation with an invisible opponent, the relentless force of friction. Ancient builders were, in essence, pioneering tribologists, masters of the unseen interactions between surfaces long before the science ever received a formal name. Their entire approach was a systematic campaign to minimize resistance at every point of contact. The most common battlefield was the interface between the heavy wooden sledge and the ground. Here they deployed a range of natural lubricants with brilliant practicality. A slurry of water and thick clay, or sometimes even animal fats, was poured directly onto the path ahead. This created a slick, temporary coating that dramatically reduced the grinding drag, allowing a sledge to glide where it once would have seized. But their understanding went deeper than just surface slipperiness. They recognized that the very shape of the moving parts could transform the problem. Dragging a flat sledge creates continuous, high-friction contact. But placing that same sledge atop a series of rounded logs changes the equation entirely. The friction becomes rolling resistance, a far weaker force. With each rotation of the log, the point of contact is constantly renewed, and the stone inches forward with significantly less effort. This was not a random discovery. It was the result of generations of observation and iterative experimentation. They learned which woods, like elm or cedar, were both strong and naturally resilient, making for ideal rollers that would not splinter under immense pressure. They understood that a pathway needed to be firm and level to prevent the rollers from sinking and creating new points of drag. This was a holistic system where the sledge, the lubricant, the rollers, and the prepared road all worked in concert. Winning this daily battle against friction was what made the entire monumental enterprise possible, turning a static weight into a manageable, moving object. This profound, hands-on science of surfaces reveals a mind that saw the world not as solid and unyielding, but as a set of dynamic relationships that could be cleverly manipulated. These monumental structures are the ultimate laboratory reports, written not on paper but in granite and limestone. The ancient builders were master scientists conducting a grand, multi-generational experiment in physics. Their method was a continuous cycle of observation, hypothesis, and real-world testing. They saw a log roll and understood the principle of the wheel. They felt the power of a long pole lifting a heavy rock and grasped the law of the lever. These were not just random discoveries, they were observations of the universe's operating manual. A team would test a new sledge design on a single block, observing how it moved over different surfaces. They would experiment with various lubricants from water to clay, noting which one allowed for the smoothest glide. A failed ramp angle that caused a block to tip would be a lesson learned, its design adjusted for the next attempt. This process of iterative improvement, of learning from every small failure and success, is the bedrock of modern engineering. It was a slow, patient science where a single successful technique might take a century to perfect and pass down. The proof of its effectiveness is undeniable. We are still trying to replicate the precision of joints that have withstood thousands of years of earthquakes and weather. Their legacy is therefore twofold: the breathtaking stones they left behind and the powerful problem-solving process they perfected. This intellectual heritage challenges our modern arrogance, reminding us that the scientific method is not a modern invention, but a fundamental human instinct to observe, to question, and to build upon what works. That final, grueling push to move a stone was driven by something far deeper than engineering. The sheer ambition of these projects points to a profound human need, a psychological engine that transformed immense hardship into a sacred purpose. A pyramid was more than a tomb. It was a civilization's declaration of its own identity, a permanent statement of power and faith carved into the very skin of the earth. The effort itself was the offering. The decades of labor, the generations of sacrifice, these were not just costs to be managed, but the central ritual of a culture proving its devotion. The monument became a focal point for a shared belief, uniting thousands of individuals under a single, awe-inspiring goal that gave their collective effort a cosmic meaning. This desire to create something that would outlive every individual, to speak to the gods or to the future, was the ultimate fuel. It was a cultural investment in eternity, a testament to the belief that humanity could touch the divine through the patient, deliberate movement of stone. The stones did not just build structures, they built civilizations, forging a common identity through shared, monumental achievement. This intangible spirit, the yearning to leave a mark that whispers across centuries, is perhaps the most powerful technology of all. From the fundamental lever to the speculative power of sound, we have journeyed through the mind of the ancient engineer. These were not primitive people struggling with stone. They were brilliant innovators who used observation, physics, and immense social coordination to reshape their world. Their legacy is a powerful reminder that human ingenuity is our most timeless tool. The next time you stand before an ancient monument, see it not as a relic of a lost past, but as a testament to an intelligence that rivals our own. We would love to hear which of these ancient techniques you find most fascinating in the comments below.